Friends, good morning and welcome you all on the last day, first session. For this session, we are with us Dr. Harvey Singh, who is a professor at IIT Ropar. Let me introduce him in a simple way that he is a friend, philosopher, and guide. Most of the faculty members in this region, they have learned many things, specifically in the area of mechanical engineering from Dr. Harpreet. He's a guiding force for how to write really good research papers for really good publication. Sir is actively involved in research with a special focus on surface engineering, degradation of material, high temperature corrosion and its protection, slurry erosion of hydraulic machines, then biomedical coating, sustainable manufacturing, technology modulation, assisted machining, friction stir welding, bioenergy generation, and many much fields. Sir has guided large number of masters and PhD theses, and I think no one in this region in mechanical is unaware of his achievement and whatever the lot of awards and citations throughout the work he has got out through his career. We have specifically requested Dr. Harpreet to enlighten us about some of the metallurgical point of view or some fabricated parts, some material process parts, so that as a material processing engineer we can really contribute in a good way. So I request Dr. Harpreet to kindly start his proceeding.
Okay, thank you, Dr. Rupinder, for this introduction, for the kind words, and good morning to all of you there. It's a pleasure to interact with such a gathering. Most of, probably some of you must be designing or planning to do some kind of research work. I am switching off my video because my signal is not great here. I am sitting somewhere in the south of Punjab. So this lecture basically, I just wanted to share with you that how a scanning electron microscope can be, useful to characterize our processed materials, right? And of course, I will present it with the help of one case study, which is on cold spray coatings, but those coatings are very thick, so thick that they can be even called as a relatively manufactured layer also, because we are talking here about 3 mm and so on. So then how to characterize that, and of course with the regard to metallurgy and some of the mechanical properties, I would like to share with you some of those insights today. So let me share my screen here with you. So I hope my screen is visible now, right?
Yes, sir. Loud and clear, sir.
Okay, and okay, now let me start. So the title of my talk will be use of scanning electron microscopy to characterize thick copper coatings deposited on SS316LG. Now here this work is basically a part of a project which was like invited project by Institute of Plasma Research, because they have some kind of very customized requirement to develop thick pure copper coatings on some of their parts. I'll just show you in a couple of minutes. So here is some of the introductory remarks about this work, because just to put the things into context. So we know there's a organization which is International Thermonuclear Experimental Reactor, ITER organization, they say. So a lot of countries are participating in it, and their mission is to produce electricity by nuclear fusion. And in that context, they are developing what they call tokamaks, which are like fusion reactors, and they would be largest and most powerful fusion devices in the world with a power application ratio of 10. Now in this, this is a big task actually. A lot of countries are participating into, it, and they are fabricating different parts of or different components of this main vacuum vessel as well as the whole system. So India is also, contributing into that, and we are working on this vacuum vessel, especially its triangular plates. Now the vacuum vessel is important because plasma operation will take place here itself, which will initiate the fusion reaction. Okay, and here we will need a lot of magnetic and huge magnitude of magnetic and electric fields to stabilize that, or this plasma. So this is some kind of a picture or photograph of our vacuum vessel. So this will be plasma here. But the work which we have been given in this project, of course, so many components are there, so many aspects are there, including physics, chemistry, and mechanical engineering, electrical engineering, and so on. We are focusing our attention on this. These are one component in this, which they call this one coil. Now here they are putting these these what they call triangular plates actually. So this is triangular support which they are providing here. Okay. And this is a further view of this this part here. Okay. Now the India has to manufacture and deliver the shielding and triangular plates in bolted packs to ITER organization. So this is what is the objective here. Now what is the specific problem here is that these have to be coated with the copper coatings, very thick copper coatings, because there will always be some off normal events. That means this radiation will be impinging on two plasma facing components, which such as first wall, diverter, triangular plates, and in vessel bed areas. So you can imagine when this huge radiation will fall on these plates, so things can go really in terms of material loss and evaporation can take place, right? And of course we are talking about very high intensity of heating loads, which is like 20 to 40 megajoules per meter square, and that too in 1 to 4 milliseconds. So we have to now passivate this situation actually. If I have to put you in simple words, so we need some kind of passivation here, so that this heat can be conducted, or even electric discharge can be made. And that's why we are talking about pure copper here, that we need some kind of, now this is again established that to improve the plasma stability, they have to have a copper cladding or copper coating, which has to be used on plasma facing surfaces of the triangular supports to improve the plasma vertical stability. So this this is like a defined problem. So we were given that you have to now develop these coatings. Okay. Now here, of course, a method for coating. A lot of people are doing a lot of work on this context, especially some Japanese groups are doing it. So they have come up with something like 3 mm thick pure copper coating by cold spray technology, and of course laser cladding is also tried. Now here the point is, of course, people have done at coupon levels some studies where they had demonstrated these thick coatings. When I say thick coatings, it's like of the order of 3 mm pure copper. The challenge here is thick coating as well as pure copper, right? So these are two main conditions in our applications. Now we know that those who work in surface modification techniques, that it's quite difficult to produce pure coatings. And here the condition is that for stability we need a very high thermal conductivity as well as very high electrical conductivity also. Only then passivation will take place and so on. So for that, purity is the concern, because pure materials can have high thermal conductivity and electrical conductivity. So surface modifications have been are being investigated, and of course when we talk about surface modification techniques, we need good adhesion strength, of course, the material, because these are like the substrate material here is stainless steel, or that we want to put this copper coating, right? So that's it's like copper is slightly softer material, but the substrate is hard, right? SS316L steel. So it's a challenge to obtain that good adhesion strength. This is one of the challenges which we have tried to solve in this study also. Less thermal effects. We don't want to temper the properties or play with the properties of the stainless steel substrate, and we need very dense coatings. Low porosity, that means we can have good thermal conductivity and electrical conductivity, and good mechanical properties. Again, we don't, because there will be some kind of load in terms of topological losses also. So we want to avoid that also. That means we need some kind of good mechanical properties in terms of its hardness and tensile properties. So India is also planning to develop fusion grade reactors in large scale with the advanced materials. This is anyway some comment that India has a very ambitious plan to contribute in this tokamak development. Now, as I said, two techniques are being investigated. Some groups are trying laser cladding. Now, laser cladding, some of you must be knowing here we use a powder or wire feedstock, and then the material is melted, and which is of course by laser heat and also consolidated simultaneously. Laser cladding, let me give you one more comment here, or thought here, that both these technologies, laser cladding as well as cold spray technology, which we have used here, both can be used for as additive manufacturing technologies. Basically, what is additive manufacturing? So additive manufacturing is something where we are developing the materials layer by layer, and some people say, okay, coating guys are always proud of the fact that they are doing this layer by layer thing since long now. Okay, so another people are now trying some interesting work across the globe to use laser cladding as a additive manufacturing technique. On the other hand, again, there are a lot of people, a lot of groups, including our group, which wants to use cold spray for additive manufacturing also. So this study, which I am going to present today, will be helpful in that sense also, that you can then, suppose you are developing a part through additive manufacturing by cold spraying or additive manufacturing, laser cladding, then how to characterize it, right? So this study will help you in that sense also. Of course, laser cladding has been used since long now mostly for tribological applications, corrosion resistance, and so on. Another interesting application is repair. Actually, repair work where we have these born out parts. Okay, so you can replace or you can refurbish those parts very conveniently. Now, there are two ways. It's just like very introductory slide here, that we have wire feedstock systems. We have these powdered feedstock, not feedstock powder systems. Okay, so we have this laser, okay, and we have this wire. So wire is fed here, and continuously it's melt, and you are making this deposition happening here. And you, of course, you have this XYE manipulations and things like that. But in case of your powder, we have these kind of torches where everything is gloved, including the laser and the powder injection system included, and then you can use it as a torch very conveniently, and you can keep on depositing the material on this surface, right? So one thing which we need to keep in mind here is that material is melted here. Okay, so whenever material is melted, we know from metallurgical point of view that we are in danger of spoiling the properties of the material, right? Of course, there are ways and means by which we can shield these materials when they are melted to avoid these oxidation and things like that. Okay, but that comes at some kind of added cost. Another thing which is happening here is that as soon as you have the melted material, so you will have some kind of heat affected zone also, and there will be diffusion of, for example, if you are developing this copper coating on this say steel material, so there will be some kind of dilution, okay, and some kind of diffusion will also take place, right, at in the vicinity of this interface between the coating and the substrate, right. So why I'm talking about this laser, even we also tried laser in our work. By the way, this is work done by one of my PhD students, Surinder Singh, who is now in Australia doing wonderful work actually. He published some very good papers out of this work also. Now here is laser cladding. Now laser cladding, as I said, one of the disadvantages we face here is this haze. So this is something which we are worried about. Okay, so suppose you deposit copper here. Yes, coating is very dense. That's not a problem. But the problem is here this haze zone which we produce. In our substrate material, right? And people have done a lot of work on optimizing these input parameters so that they can reduce these depth of these this is depth of haze, right? So they have given this nomenclature. This is height of this bead and width and so on. No, you can see here that people are trying different types of laser power, scanning speed, feeding rate, etc. to decrease the effect of this haze. Okay, so it's like 10.8 they have reduced in this number 3 case. So basically this is by playing with the parameters. Okay, so what it essentially means that when we were doing this work, there was a lot of discussion on this, that some people are really in favor of using laser, and they always put claim that they can reduce this haze to bare minimum. Okay, and this is the evidence that yes, there is a chance that we can reduce it. Okay, but then there are some other problems also which we will I'll try to highlight as we progress further. Now then, talking a little bit about the second technology, which is cold spray technology. And this is technology which even Japanese group are endorsing it very in a big way. This is some Fukunawa's group, so they are out for it. Now let me give you a quick overview of what is cold spray here. Now the objective here is, again, we want to deploy this material on this substrate material, right? Now what we do here in this cold spray system is that we propel the particles at very high velocities, okay, and so that they go with very large kind of kinetic energy and impinge on this surface, and they plastically deform and they got stuck there, right, on the surface. So it's like converting whole of this kinetic energy into deformation energy and some heat energy also. In fact, there is a lot of discussion on how the material sticks on this at micro level and so on. And we also added some insights through this study. I'll share with you that. Now here, when I say velocities, so I am talking about essentially supersonic velocities, means we are more than 1 Mach number, right? So those velocities are produced, and of course, to produce those velocities, the idea here is that we have the one working gas which is accelerated to supersonic velocities, right? And we know that to accelerate the gases to supersonic velocities, nozzle convergent, the divergent nozzle can be one very good example here. For example, here they are using. So in all cold spray processes, we have this supersonic nozzles, what we call, and we propel our gas through it, the working gas, which is usually nitrogen or helium, and that gas is then fed here actually, and which is then expanded through this, and we achieve this supersonic velocity jets. While doing so, we also introduce the powder particles into that gas stream, and they also get momentum from the gas, and they also get um, accelerated towards the substrate. Okay, and of course we heat this gas to decrease its weight, so lightweight can travel at high velocities, and of course for some thermodynamic reasons here, that we know that as soon as this is the throat, right, this when the material will, or sorry, the gas will exit this throat, so we will have all of a sudden kind of drop in temperature also, right? So to compensate all those things, we heat it. So we heat the gas, and of course just this is our powder feeder, so powder is fed from here. Again, it is heated to some very nominal temperature just to remove the moisture, etc., and then it's propelled through this thing. Now the beauty here is that we are not for example, this is our copper powder, so we want to propel it on the surface. So the beauty here is that we are not heating the copper powder, okay, which is which makes it like a kind of what they call a solid state process. And we always love solid state processes where there are no high temperature involved into it. So that's what is shown here. So cold spray is getting kind of recognition due to this very property that it's like a solid state process. Some temperature sensitive materials can be deposited very easily by a cold spray process without damaging their metallurgy. That's what. And that was our condition also, that we wanted to have pure copper coatings, right? So copper is also susceptible to oxygen oxide formation. So that's what happens. Now, these are typical values you can keep in mind. Powder particles are also typical in the range of 10 to 40 micron and so on. And here what happens is extreme and rapid plastic deformation. I said it's like your particles are going at very high velocities. So you can see the deformation level or strain rates which are executed by the material are much higher, okay? So it's like severe plastic deformation process. And of course, when these particles go away, they even disrupt any kind of layers on the surface itself. So this manipulates in terms of that we need lesser surface preparation for our substrate materials for coating deposition. So a lot of benefits people are claiming through this cold spray process and so on. See, the deposition efficiency is also sometimes very high. Now, all these advantages and our prior work in thermal spraying and then cold spray inspired us to write one project, and we got this cold spray equipment at IIT Ropar, which is a kind of one of its kind. Now we have two such systems, one in IIT Madras and one in IIT Ropar. Simultaneously, we installed them. The beauty here is that we can go up to this pressures of 50 bar. You can see plus 50 bar, which is very high pressure, right? And temperatures are also 1000 degrees Celsius. So this is the beauty of this system. It's not that we don't have cold spray systems in India, but having these kind of capabilities in terms of 50 bar pressure and temperature are very less here. At least I know only two. One, of course, is there in GE and some private things like. But in public sector, I can have. I think we have only two such systems which can go up to this. Now, when we have such a high pressure, so we can then we can use it for additive manufacturing also, because what is additive manufacturing? Basically, if I keep on increasing the thickness of this layer, so I can go to produce very thick components, right? And if I can manipulate this gun to produce some kind of geometries, right, It's just like a spray gun here, which is manipulated. Of course, it's manipulated by this robot here, because this is quite heavy. It's like 40 kg, and if we can manipulate it in in this fashion, we can raster, or we can say have secular parts and so on. We can produce some standalone geometries as well. So that is the inspiration here, that since pressure is very high, temperature is there, so we can keep on increasing the thickness of this layer, and we have developed layers up to say 15 also in our lab, which is the kind of hope that we can develop some standalone geometries as well. This is powder feed system. This whole system is installed in acoustic chamber. Why? Because, as I said, we have something like aeroplane in our lab, right? So you can't afford this noise to be there. So that's why everything is done in acoustic chamber and so on. So this is the facility which we used. Now coming on to our back to our understanding. So why this SCM? As I said, SCM we have used basically to understand the adhesion mechanism. Now, adhesion mechanism is a challenge, right? So still people are debating how things happen. So, one thing is that we will need some kind of critical conditions for this extensive plastic deformation at the interface. When the particles come here, for example, here you can see this is a SEM image, right? So here there is no particle, but here is particle, right? So we defined something we call critical velocity in this our cold space system, when the particle will stick on the surface. Otherwise, it will either rebound or it will go and erode the particle, substrate and go away. So that is something which is a necessity here, that for any given set of materials, substrate materials and coating, you have to find your critical velocity. Okay, so that's one thing which is very important, and that varies actually. That varies with the material combination, right? So that I think we can understand, because this deformation levels will depend upon the type of materials and so on. So some people say much localized heating near particle substrate interface takes place. Some people say a particle will come here. Okay, for example, this is some simulation, and this is some experimental work done by some group. So here they say that when the particle comes here, it deforms, and this is like, it's not that the particle only is deforming, it's also substrate which deforms, and you get this kind of bulging out of the material, which we call this whole thing is known as jet formation in our this one. So people say that this kind of jet formation should take place at the point or at the interface. There is hardening effect also, right? So it's like a short pinning. This surface can get hardened due to state hardening and so on. But at the same time, softening also takes place. This is what I'm saying, that there's a lot of debate, a lot of thought processes are going on to understand these kind of adhesions mechanisms. So there is some people say it's like adiabatic shear instabilities which give rise to this bonding mechanism. Okay, some people say this is the jet type flow and so on. Now in adiabatic shear instability, they say that at very high velocity shear strength falls to zero due to thermal softening dominance over hardening, right? And there's higher heating rates inside the particle due to shear plane failures. So then the particle, just like it flows, right, to impinge on the surface. And some people say balance forces or interlocking forces or both are there, right? So some people say it's like a metallurgical bonding, some say no, it's only mechanical and so on. So people have done a lot of interesting work through SCM. So these are again SCM pictures, right, taken. And this is like they will coat copper on aluminium, and then they will do its shearing, okay, and then they will see if there was some these kind of signatures were present and so on. In fact, this is the approach which we also followed, but we showed some more in-depth things here. Now, another aspect which we have, which we have investigated in this, is the substrate conditions will also, dictate the adhesion strength. So there are different types of, thought processes that how the particles, impinge on the surface and how they get locked on the surface and so on. Now, in this case, then these are some of the models, interesting models from our literature. So one thing is that we can have different types of materials, right? We can have rigid particle and soft substrate. Now, if this is the condition, so if particle is almost rigid, then this kind of sticking can take place, right? The deformation will be only limited to the soft, substrate, not this one, okay? But then there is a plastic particle on soft surface, which this can be a condition, something like this, okay? In fact, this is something which is very easy to quote. And then we have plastic particles, but rigid surface. So there, the particle deformation will take place more. These are more like idealized conditions here. But there is a lot of discussion on this, that if we have rigid surface and there is a subsequent, there's some amount of roughness is present on the surface, then it is very convenient that we get this kind of sticking very nicely. So they say sharper peaks don't deform at impact. They introduce more deformation and mechanical bonding in the powder. But there is no evidence, and there are a lot of contradictions on this. Basically, this understanding came from thermal spraying. In thermal spraying, where the particles are heated and sometimes melted, in fact, most of the time they are melted, there this hypothesis is good. But still, even in cold spray groups also, some people say no, it's good to have surface roughness. Some people say no, it's not good. For example, this there is a interesting study by this I think Kumar et al, which only studied the effect of this substrate conditions on adhesion, and there he saw that even the finer surfaces. This is 220 grit, right? So much. So this is the more finer surface, right? This is blasted. Blasted is more roughness. He saw something opposite from this. Okay, he said that when we have this more polished surface, the chances are that we get good deformation. But again, some more insights were needed, so that's why we needed this. So these are substrate conditions. Again, continuing, I think I have talked about this in the previous slide. Another aspect which is very pertinent to our coating or even additive manufacturing is post-heat treatment, right? So here, see, whenever we play with the powder particles, which is usually the case in additive manufacturing also, so we are always worried about these flat boundaries or the points where the particles are, sticking to each other, right? And that can be improved, of course. Porosity will also come up when we don't have, heat treatment and so on. But when we do heat treatment, we know from our basic understanding that we can have, kind of better adhesion. So because these flat boundaries or particle boundaries, they will merge, right? And we will have something like, what we call grains, better grain structures with lesser porosity and so on. Okay, so this is something on that heat treatment is also frequently considered, and which can also give rise to adhesion strength due to recrystallization and so on. Well, this is anyway. So what was I think I have talked about this, but let me tell you that just to make it more systematic to understand, that we were developing 3 mm thick copper coatings. Okay, so which is a challenge, let me tell you. And especially when we say it's like a 5 meter into 1 meter long plate, right? So that is something this much. Another thing is that there's limited work on effect of substrate roughness on the adhesion strength. As I said, there is a need to do some kind of more studies. Another thing was that since we did a lot of work on this, our objective was to achieve the adhesion strength. So we tried different kind of strategies. One strategy is usually introducing some interlayers actually between cold spray and the substrate. This is another technology kind of thought process which are given by one of the scientists in IPR, and we tried it. He was expert in our panel, so he said, "Why not we try this?" And it's like using some kind of bond coat between two layers, right? So we tried that also, and some interesting results were found. Uh, and of course, substrate temperature on adhesion strength and so on, and bonding mechanisms are still not formed, I would say. This was the research objectives. Very clear-cut defined problem was given. So here our aim was to produce coatings of 2 to 3 mm and adhesion strength of the order of 56 to 59 megapascal. This is really uh, a big value, I would say, which is there. And porous TC, we need 1.3% less than that. So tensile strength was again much demanding, and so on. Okay, this P should be capital anyway. Electrical resistivity was there. So this everything was defined, and our objective was to achieve all these things, and that's why we have to do a lot of hit and trial and different technologies to arrive at these parameters. These were not that easy, straightforward to arrive at this. This is the methodology here, which we have used. Of course, material which we have used is, as I said, our objective was to achieve pure coatings, right? So that's why we purchase this pure copper powder, and of course, substrate is this, and then we. This is our parameter selection, and so on. I think we can skip this. And cold spray coating development we did, and here we, as I said, we have different types of two things we tried here in this work. One was that introducing some interlayer between them, and that interlayer was developed by this electroplating route. Okay, now somebody may say, why not use electroplating throughout for 3 mm? So it will not be that easy, right? So we will not be able to achieve 3 mm by electroplating, right? So, but we can always achieve few microns of electroplating on the surface, and then start depositing cold spray coatings of the copper. And that's exactly what we did, and that gave us a kind of good results. The second strategy which we tried was roughness. So roughness was varied on the surface, and then we tried to deposit the coatings. And third thing which was done, that we tried some post heat treatments. Okay, and even preheating of substrate during coating was also done. You can see a lot of effort went into it when we talk about, right? Now, this is our prelim work. In prelim work, what we did, because some experts were of the favor of this laser cladding, so we even developed this by laser, cladding also. Okay, so some of these parameters, of course, it was done by some commercial unit in Bangalore. So he used some of these parameters, and we could produce this one. But at the same time, we develop these coatings through air through cold spray process also, right? So here this is the standout distance, and initially we started with 15 bar and 400 degrees Celsius temperature. At that time we were not having this high end system, so we took help from ASCII Hyderabad. Thanks to them, they developed some kind of coatings for us. Okay. And but things were not in place, right? We used these parameters, but still adhesion was not up to mark. So that's what we saw here. So although you can see here, coatings were could be developed here. Okay, thick coatings were developed on these plates. Okay, these are anyway, these are the XRD images of our powders, feedstock powders. Just for the young people, that whenever you get some powders or some feedstock materials, you must characterize them, right? So we never knew what industry is going to give you. Okay, so whenever you start your search, you have to characterize your materials and so on. So they were saying it's like a spherical morphology. So SCM has been used here to see the morphology of those particles, and XRD has been done to see this. Okay. In fact, XRD and SCM, these are two very frequently used technologies which help you to study the metallurgy of your parts. It may be additive manufacturing part, or it may be some coating and so on, or some processed material. Now, this is what the result of our prelim experiments was. This is our this is cold spray, and this is our laser cladding, right? Now in laser cladding, so these are cross-sectional images by SCM. Again, SCM helps us to take surface pictures as well as cross sections. Very nicely you can identify different regions in this one, right? So this is, for example, here this is cross section. So we have this substrate comes here, and then we have this copper and oxides, and here we have this hatch zone. So you can see we see a lot of hash zone in our laser cladding. This one, okay, and it was like large hash, but there was no gap. Adhesion was good. That's not a problem here, and that's what. But when we tried through cold spray, of course, copper plus oxide. Somebody may ask you, how did you arrive at this? So we did XRD of this, right? And here, so we have this coating of pure copper. We did the XRD, and we see there was no oxide, right? So we could get very nice. And this was interface region, and this is our substrate. Now here, see, this was a pore addition actually. So there was a kind of gap at the interface, and which is worried for us, worrisome for us, that we have to do something more to achieve it. So both have their own disadvantages here, and of course this was not our solution, right? And the same coatings, we tried XRD, micro hardness, and so on, right? So we tried that, and in laser cladding, so it's like softening of substrate near interface, hardening in hedge was observed, coating is harder than the cold spray coating, and so on. Hardening of substrate very near to interface takes place. This is like impinging, so since these particles, they come and impinge on the surface, right? So they expose your material, substrate material, to some kind of strain hardening and so on. Coating hardness was less as compared to has. Anyway, these are more kind of detailed information about this. Because this is like coating hardness is less because it was a pure, but here we were having some kind of oxides also in the material. So that's what. This is more see how beautifully Surinder has taken the pictures by SCM of different zones of laser cladding, because we face tough time to convince people that no, laser cladding is not the right solution, right? So for that we did a lot of studies, right, along the cross section at different points and so on, So we could see all these kind of grain growths and unnecessary grain growths, I would say. This is again SEM picture, but this is optical picture, right? So you can see this grain growth and all kind of stuff happening in the material, which is not appreciated by surface engineers usually. So heat of new layer increases the grain growth. Even we try to give some kind of reason why it is happening, that there is a quite grain growth here. So we could see that because uh, these coatings are developed layer by layer, right? So once you deposit some layer, say 20 micron, and then another material is deposited, right? So every time the previously deposited material executes some kind of temperature cycles, and there is a chance of grain growth and so on. So that's what is shown here. So SCM could reveal this nicely. Okay, this is etched one with SCM, and you can see this. Now, this is these are the results actually: laser cladding and cold spray. It's again the prelim experiments which we have done here, right? I have not come to the final, the better ones. Now here, these are thickness ranges of coats and so on. So these red things are something which we could not achieve, right? And that makes us that we have to do something more on it. Okay, and see here the laser cladding and this thermal conductivity and this electrical conductivity. See, electrical conductivity we could achieve even with this one also, because it's a pure copper, right? So we could achieve that. But then there was some kind of other problems, porosity and so on. Porosity was good, but this one, elongation was also some kind of limitation and things like that. So what we decided at that point of time, that we are getting some kind of hopeful results in terms of thickness, porosity, which is one of the major concerns, and our electrical conductivity, and even thermal conductivity was not bad. So we thought of that we should optimize the parameters of cold spray system and so on. So that is where we started, this work. So here we then took, even that time our system was not in place. We took help from GE to deposit these coatings at 50 bar. So you can see this 50 bar is the critical point here. So pressure has been increased tremendously. Earlier it was 15 bar, now it's 50 bar. And standard, this is, and temperature was also high here, gas temperature, right? And then we could deposit these coatings. Okay. Now what we have done here is we have taken as three conditions. One is as received, means the surface roughness RA value, which is represented by RA value, was like 2.5 in one case. Then we have a semi-polished samples, which is like 0.5, and this one is 0.6, right? And this is the as before coating hardness. And anyway, so roughness was varied here, right? So then we can produce these three types of now here. Let me now start. Right now I will spend some time on surface roughness effect, right? So we have tried here three surface roughness levels of what? Of the substrate, right? It's like you will prepare the substrate with these values of surface roughness, and then you will start depositing the coating on the surface. That's what I mean. Now in this case, what happened was that when we started depositing coatings at three conditions. So this is first one where this is like roughest surface among these three. This was a medium, and this was a mirror, or this is not mirror, I would say. Yeah, it's a mirror polish. Okay, so it's a very pretty polished. So this sample is polished. This is as and this one. But now these are the real samples. Now you can see here readily that this in this case even there was no adhesion actually. As soon as we deposited this layer, uh, sorry. So as soon as we deposited this layer get out of its substrate, right? But here it was sticking. It was sticking here also, right? And then we took this. This is a kind of NDT, this ultrasonic setup, by which we took some idea about the adhesion. Now here, this was. So this is like a back echo. So here you can have these magnitude of these echoes. They represent some kind of debonding. Okay, so we get some more debonding signatures in this case compared to this one, right? So this is the first indication that we have a good bonding in this third case. In other words, mirror polished sample was giving us better bonding than this one, okay, which is contrary to that hypothesis of having more hardness, surface roughness to get better this one. But then the question was that we need to now establish that, and that's where I think Surinder has done good work, which was published. Anyway, before that, these are some properties which we could achieve with this one, okay, and these red marks are basically after heat treatment. As I said, we varied the surface roughness and we produced 3 samples, right? And then we did their heat treatment also. And that's what has been done here, right? So you can see here, this is as separate coating. This is heat treated. This is one sample which has been shown here. I don't know which one it belongs to, but you can see that this merging of these supplat boundaries. Usually in cold spray you will see this kind of microstructure typical, but then these are getting merged and you are getting this more dense structure, right? Granular structure after heat treatment. And you can see here in all cases the XRD is not giving you any kind of oxide, which is something which we were looking for, right? Now these are further cross-sectional SEM images. See how beautifully SEM can pick up these cross-sectional details. Okay, so this is this one, this one, and this one. Okay, so and these are heat-treated cases. So these are as separate coatings. These are heat-treated. So you can see merging of these splat boundaries taking place and so on. Okay. So this is our third case. This is a mirror polished case. Okay, so you can see some indications here in this these images by SCMC. When we say it was like a mirror polished, so you can see this substrate surface is smooth here, but here it is more like this, right? Here it's like only layer. Here there's no coating because coating got detached from the substrate. Okay, it was just like this case. Okay, but we still intended to see what is happening to this structure, so and so. And then micro hardness and other properties we evaluated, and we can see these values be achieved, right? So, and hardness and so on. Okay, now this is what the hope. Young's modulus for SC2 specimen was comparable with bulk. What was this SCC2? Means we have applied the this heat treatment also on this mirror polished sample. So in other words, our recommendation from here went in the form of that if you want to deploy this coat or achieve this kind of coating, then you have to first mirror polish the sample and then deposit copper on it and then go for heat treatment as per our protocols. Okay, but still, still we are not able to achieve the adhesion strength even in this project. We have made some recommendations, but still we have not achieved that much adhesion strength. Now anyway, coming back to context of our SCM, and to understand the role of this surface roughness to some better depth, we did this lap shear test, what they call. Now here what happens is that consider that this initially this is same, this is here, right? In lap shear, what we do, we may cut here and then we pull it right in this direction, so that this section is under shear now. Okay, and when this material gets, so we get what we get two kind of aspects. One is coating, another is substrate side. No? So when you will pull it down, you will get this export surface, which was earlier coated, but now no more coating is there. And then this was coating, which was already very much sticking on the surface, but now you have detached it with the pores, and then this surface. And that is where we did this SCM. That what is happening at these surfaces, right? This surface and this surface, perpendicular to this slide, you can imagine, right? So that gave us very nice kind of thought process. Surinder did this. Of course, in literature, cross-sectional images were there, but Surinder did the surface images of these fractured surfaces. So one will be steel side, other will be copper side, right? So when I say copper side is this one, and substrates or steel side is this one. Okay, so lap shear you did, and then you took these images here. Now these images look something like this. This is for the first case where surface roughness is of the order of 2.5 micron and so on. This was the second case. There was no bonding, but still we took the pictures. And this is the third case where there was a lot of adhesion we could achieve. Now then we started wondering what these kind of structures they are signifying, right? When I say this kind of structure is there, so some kind of matching things are seen here. See, in SCM, quite often my supervisor used to tell us that more you see or more you spend time on SCM images, more information you can get, right? Keep on sitting with them, sitting at them, and thinking what is happening and what are the features and so on. Okay, so you will see in this case it was then we started wondering what kind of these features are there. These are like dimples, right? So, and this is steel side, this is copper side. So here there was no adhesion in this case, right? Here was it's okay adhesion, but this we call best adhesion, right? Now here there is some different kind of features. So now the way forward for such kind of thing is that we all know that SCM can give us the morphological things, but if we want to get some compositional aspects, you have to do what you call energy dispersive spectroscopy, and that's what we did. And that was something which gave us further understanding of what was happening. Now this steel side is also having copper. This red is copper here. If you see, these are EDS images, these two, right? These surfaces, we took the EDS. EDS is now giving us the element distribution of several components or several elements, which further gave us an idea that what's happening, right? If you see this one, copper side means coating side. Ideally, everything should have been copper, right? But there are these pockets. Now, in these pockets, that means copper has got detached with the while it was lap shear. So that came here actually. So that means that is giving some kind of this information about jetting thing, which is that there was some kind of merging of this copper into the steel side and both vice versa. And when we broke them in shear, so these elements were shared between them, right? So this gives us an idea about the jet formation, and even metallurgical bonding indications. This one, right? But see this case, again, amazing. In this case, there was no kind of bonding between the copper and the steel side. It is just like we took this and we took their SCM and EDS. See here, we don't have any signs of our copper. That means it's whole steel and it's whole copper, right? Copper side is whole copper. Copper here is this bluish. So that essentially means that nothing happened actually of that sort, this sort, right? This sort between these, and that's why there was no bonding at all. But then this is the most beautiful case, the best case in this case example. So here, see, this all structure is now giving us this is steel side, this is copper side. So you can see copper, a lot of copper in this one, right? In fact, these are copper, and then we have this kind of bonding between these two. Okay, chromium or Fe was seen from our substrate in this stage. So a lot of indications of metallurgical bonding, of jet formation, and so on. So here again, this is just for extension that a lot of groups are kind of arguing on these that what is happening. Smith and this Gangraj and Hassani. So they have, we were like in line with their ideas, but then Asadi and there's another group, they have some other thought process in this. Anyway, so the bonding we could see, we could establish through SCM images very nicely. That is something which is there. Now, then another interesting thing which Surinder has done, I really appreciate, is that this is basically, they call it single particle deformation behavior. In this case, this gives very interesting results in the sense that you can get idea about how one particle is interacting with the substrate. Right? In this case, what they do is they simply, in one go, they will quickly pass the gun over the surface, substrate surface, and some particles will, deform on the substrate, and then they will take their images, SAM images. So this is again very well appreciated kind of approach that we investigate the single particle deformation behavior. So here Surinder did it, and he again took these SCM images. So you can see a lot of SCM. He spent a lot of time on SCM, and that's very appreciated because SCM taking these images, choosing these points right on the sample, and then taking images at right magnification and so on, it makes you sometimes frustrating because a lot of time goes into it, and you will need a lot of focus to achieve these things. Now here what he saw in the as separate, he saw these particles. Here again in semi-polished, he saw these images, and mirror polished, he see these cases. Now here, although SCM is SCM is not very accurate thing to give you some depth information on the surface, but still some kind of sense you could get here, right? So so if anyway, let me go to the next image, which is this one. Now this is, he took the profiles of these samples. Okay, it's like moving the profile over like this surface, okay, which covers this substrate maybe, and then particle will come and then he takes. Okay, and when he took this kind of profiles, these profiles, okay, he could then find out the information about the depth of the particle inside the material, or I mean about the penetration of the material or the particle into the surface, right? So that's what. So from here it is visible that in this case this was like quite smooth as compared to this one and this one. What essentially it means that the penetration of particle was very good in this case, which was the mirror post case. Okay, whereas here it was some other problems, some even deformation in the neighboring areas. Particle is not entirely into it. There is a height, and same is this case. But then he didn't stop here. He having some idea that okay, penetration is fine in the mirror pulse thing, but then what is happening at the cross section of these particles? Then he took these cross sectional images. I really appreciated him for going so deeper into these things, and he could then see the adhesion at the interface of the particle and the substrate. Now, see these three cases. In the first case, okay, they call insufficient deformation, deformed copper particle. This is copper particle, this is the substrate. What is this image? Basically, it's like cross-section image of these, right? So he could see that something was there, right? The interface between particle and this was not good. There was still a gap. Although these peaks, these things, these fragments have been deformed, okay, but still there's a gap. Okay, so what are these materials? These may be the hills on the surface of the substrate. So when the particle comes, now this has a sufficient kind of surface roughness, so we will have some valleys on it. Then the particles will come, impinge on the surface, and they will try to deform these hills, but these are not completely deformed. Okay, and that is why, or complete deformed, or no force is sufficient force is not there to fill these gaps. Similar was the case here, which is even worse than this. So you can see in the second case there was no better adhesion. So these sharper peaks, they deformed, but still they are not allowing this copper particles to merge with the substrate. But see the last case. Here the penetration is perfect. Penetration is perfect, and even you can, from SEM image, you can even now make out whether these are two materials or not, right? So they have just become one part. And when he did the EDS of this, he can see this is the EDS. He could see very nicely it's a copper particle sitting in the substrate here again, and even this jet formation kind of signatures. Okay. So these results were in line with Hassan et al, but contradicting this one. Anyway, so this is another thing. Then we have mechanical characterization of these samples. Anyway, he did this SEA. In fact, we evaluated the tensile strength in both the modes, in macro mode as well as in micro mode. Okay, and we could achieve some values. But this is what I want to emphasize here with regard to our characterization through a new, not new I would say, but slightly kind of less used technology, which is in situ SEM, right? Fortunately, we have one setup, very small setup or attachment to our SEM, which can be placed in the SEM chamber, and you can prepare the bone shape, dog bone shape samples for tensile testing, and you can see online what is happening, right? I mean, in situ, you can keep on capturing the figures as soon as you are increasing the load on the sample, right? So this is some exciting thing, and this gave us a lot of again insights. So for example, this is say any one, you can choose the stress strain curve here. Or along this curve, you can keep on capturing these pictures. For example, A point, B point, C, T. Accordingly, here's A point. At A, nothing has happened, but at B, you can see some cracks have started developing, right? And then C, further growth, and D further, and E, and yeah, F is again some here. Anyway, this may be some other material, but you can see then the crack is grown and it's like a fracture here, H. So what we saw from here that two things. One was, of course, the values in micromode. These were slightly, higher. Okay, we explained it anyway. That's possible actually when we study the material at micro level, so they can give better, properties, which happened in this case. But more important thing here is that we can see the crack growth. Actually, crack was taking place along the splat boundaries, right? So these cracks are, developing at the intersections of your splats, and then they form, then they grow. But they are hindered by these further other splat boundaries also, or splats, and then they divert from that. For example, this group starts here, and then it along the splat it went, and then it goes like this. So this, based on this, again, it's again how much time you spend on this aspect to explain how these cracks are moving. So basically, these cracks have developed at the places of junctions of multiple splat boundaries, and then they grow and so on. Again, beautiful use of SCM here. Anyway, I think this is this is what we have already seen or explained here. I have talked about it, but another thing is this one, that even Surinder did not stop. He because these coatings are to be used in these radioactive environments and so on. So he even did these radioactivity tests of the exposure of these coatings in some lab in Delhi, and we can see that the coatings they sustained very well. And again, once we expose them to these radiation loads and so on, we saw them through again SCM to establish that nothing has happened to these materials. And we could recommend at the last that that if we want to go with this approach, so we have to mirror polish the sample, and we have to do the heat treatment of the sample, right? This is the second approach. As I said, we tried two approaches. One was this surface roughness, playing with surface roughness. Another was this electroplating effect. Now, in electroplating, again, we used two techniques in terms of this electroplating layer. In one case, we tried nickel electroplating, okay, and in other case we did what is this copper electroplating itself. So, and that's what it's copper or chromium. Let me move further. I'll clarify out. But the point was that the interlayer was, the composition of interlayer was also changed, and that's where I would show you that how it helped. So these are not SCM images, these are optical images of our coating with these layers. Okay, and this is first case is same case. There's no interlayer between them. Okay, as cast but here it is coating. So we have some layer here, but in this case it's quite visible. This nickel layer is We can see this nickel layer is here. Okay. Yeah. So it was a copper layer, right? Okay. This in second case was a copper layer. Anyway, so the this is again SEM images. These are SEM images. Here there is no interlayer. Here it is an interlayer of copper, but here it is interlayer of nickel. Okay. Now, and these are after the heat treatment, because heat treatment we have tried in all the cases. Now, see here the beauty of again SEM media. So we could establish, because how to establish, because from this SEM where you will never be, it will always be arguable that whether it is real nickel or not. But when we do EDS analysis, you can see this layer very clearly. This nickel layer could be seen. Okay. And similarly here nickel, in one other case nickel. This is another case. See, this case basically refers to this one itself, because one was the one of the practical challenges was that this we wanted to deposit the interlayer of copper, but copper cannot be deposited on substrate through electroplating directly. So that is why the industry suggested that they usually do it with the help of a copper. First, sorry, nickel. First, they introduce very small, thin layer of nickel, and then they attach copper on it. Okay, so this enhances the affinity. Okay, so nickel, chrome, this copper don't have what they call affinity towards steel, for that matter, right? So that's why nickel was introduced in both cases, but here it was very thin layer, but here it's very thick layer. This is referring to this third case. I'm sorry, let me clarify this. Okay. These are again combined composition images by EDS. Okay, this shows very nicely that where is the main copper, nickel, and this is the steel, and so on. These are the lesions here. You can identify the this matter. Now again, in this case, what we saw was that in third case, the bonding was very well. Third case means where we introduce our nickel interlayer, thick nickel interlayer, not with the copper. Okay, and that's what we will see why it was. Because the next question was why it is happening that with this copper we could not get better, right, adhesion. Whereas with nickel, we could achieve very nice. You can see there is no significant peak, and red shows some kind of loose bond here in these scans. So here there's nothing, and we could achieve very nice properties. And now this is what is our single particle deformation in this case, behavior in this case. Now, let me again tell you that in the second case where we have this copper interlayer, adhesion was very poor. Okay, even it was broken with, or it can be detached with the hand itself. So that is where we started again wondering, and this single particle behavior gave us again nice insights. Okay, so this is first case. Where this I have already shown you in the previous case also, but in this is the last case where you can see very nice kind of interaction here. This is our nickel. These are single particle, right? In fact, and these are their cross section images. Okay, let me again clarify here. So see this last case. In this case, this is our substrate, this is our nickel interlayer, and this is our copper. See how beautifully the bond has been seen here, single particle behavior. But here there is a lot of gap. Okay, and Why? Then we wondered why it is happening, right? The point here is, in this case, is that where there was no adhesion, the copper interlayer was, we have seen that it was not having that mechanical strength. Actually, it broke away. You see, this is also copper electroplated. And when we introduce this one, this is our particle which is coming through cold spray. This interlayer, electroplated interlayer has gone away. It has broken and particle has further penetrated, and then this one. But here we have not seen that because nickel has high strength. So nickel could sustain here nicely and could host this copper nicely without getting deformed much. So, and this is this referring to this one. Okay. So that is where we have concluded that even copper interlayer was not helping us, but nickel interlayer helped us to host these layers, subsequent layers of copper on this whole system. Then, of course, we have this mechanical characterization again. Stress strain curves. We have seen these again. It depends upon you guys that how nicely you see these, how nicely you introspect on these curves, right? So Surinder might have seen these flattening of curves, and he saw that, and then he tried to correlate it why it is flattening. So he says the flat zone due to sudden failure of flat boundaries in the vicinity of the originated cracks and so on. I mean, these are more insights you can keep on concluding from these. This is again the same thing performed on these coated layers with interlayers of nickel and copper, and you can see again these how failure is taking place. So crack originated from coagulated splat boundaries and grows along the splat boundaries, and some cracks were hindered by 90-degree splat boundaries, and from there they get diverted into some other directions, right? And so again, the developed coating could sustain well in nuclear as well as high heating load environments. Let me tell you that he even all these coatings were tested under cyclic conditions at 1000 degrees Celsius also. That too for something like 50 hours of cyclic loading and so on, so that we can show that they will sustain in those environments. So this was the recommended thing here, that this is the second approach by which we can prepare the required coatings for our application, where we will have to introduce nickel interlayer, and then followed by copper coating, and then followed by heat treatment. Okay, that will give us a nice solution to this problem. Now, yeah, this is what, and if you have to ask me which way we can go ahead, even among these surface roughness and electroplating thing, because somebody asked me this question sometime, that now you have suggested two ways to go ahead with them. So I said, although it depends upon the facilities which are available with you at that point of time, if you can introduce surface roughness easily, it is fine. But if I see electroplating route is also pretty well in that sense, because now electroplating processes are fairly well established for 5 meter into 1 meter kind of areas. So probably it will save more time, right? For example, if you have to introduce surface roughness on or mirror polished surface area which is 5 meter into 1 meter, it will take long time. Okay, but electroplating can have a better production rate and so on. Thank you very much. I think I have done my part. So Let me see if there are some questions. So this is what I wanted to say about this topic today.
Okay. Thank you, sir. Thank you very much, dear participants. Now the panel is open for discussion. Any questions from the participants? You can also put your question in the chat box. Any questions from the participants, please?
I hope I was audible throughout the lecture.
So, yes, sir, totally loud and clear, sir. It was very clear.
Anyway, I would invite, if there is, you are always most welcome to visit our lab. It's like your lab. Our name of this lab is your lab, actually. So you might have seen on some of the slides, right? So you are always most welcome to visit us and make utilization of this facility. So you can always discuss. You can always write me your questions or concerns, because it's ultimately from these interactions that we learn from each other. So never stop interacting. Yeah, that's what.
Sir, we are finding some difficulties in this metal-centered parts, specifically in their characterization. And but what we observed with the metal-centered parts, specifically if they are of 17.4 pH stainless steel or SS316L, we are not getting the microstructure that as per the conventional process we are getting. That is the one problem we are observing.
There may be some you want to say you are taking optical images and you're not getting etching properly, right? Okay. It's about etching. Huh?
Okay.
So etching agents may be studied further. I don't have something right now in my mind, in my brain. So that is one thing that there specimen preparation is very, very critical in all these cases. So sometimes we end up damaging the grain structure and so on, and then sometimes it's like a few seconds more of exposure to etchant spoils everything. So why don't you first take some idea from SCM images and then slowly move into this one.
We will discuss the specific problems with you maybe after discussion.
Okay.
Okay. Anyway, so if there are no queries, let us thank Professor Harvey Singh for sparing the valuable time for this discussion. I think, sir, there is maybe some personal request to you.
Yeah. Postdoc, actually, postdoc, you can always, let me tell you, show you the picture. The funding is becoming scarce now, especially due to COVID. But we should try postdoc positions with the funding from DST or some other agencies. And for that, I can always host you. For example, this DST, National Postdoctoral Fellowship Program, is there from DST. A lot of people apply every day, every time. So, Durg Prasad ji, you can also try with me. I am ready to be your mentor. That's not a problem. But in institute right now, I think we don't have any positions, mainly due to this COVID restrictions. We don't have funding for that. Yeah. Okay.
Anyway, thank you, Professor, for coming to this session and giving us the information in this area so that we can really use this basic information and can apply in our material processing way. Thank you very much.